Am I audible? Am I audible now? Are you able to hear my voice? Are you able to hear me? Just type here if you are able to hear my voice. HEAR here. So is there any disturbance? If you are able to hear my voice? Disturbance is there? Okay then, shall I start the class? Okay, so if there is no disturbance, I will start the class. I hope there is no disturbance. I hope there is no disturbance. I will start the class. So once again, I'm starting with the beginning. So principle of operation of DC generator. So principle of operation of DC generator. So whenever a magnet is moved around a conductor, magnetic flux lines are cut by the conductor. Or conductor cuts the magnetic flux lines. So EMF is induced in the conductor. Or if conductor is moved in the magnetic field, you can see a magnet here. So the conductor is moved in the magnetic field. Then also even then also what will happen is EMF is induced in the conductor. So when EMF is induced, if the conductor, you can see here, if it forms a closed path, current will start to flow through the conductor. Okay, this is our conductor. So here I am showing you a single turn conductor. This conductor has a single turn conductor. Conductor can have n number of turns as shown in this diagram. Conductor can have a number of turns. You can see 3 turns are there here. So when conductor has a number of turns, you should call it as a coil. Okay. So different conductors are interconnected together to form a coil. Okay. So here this coil has 3 turns. So let us see the working principle of this generator. So the working principle of the generator is, principle of operation of the generator, not working. Principle of operation of the generator is based on the Faraday's law of electromagnetic induction. So whenever number of magnetic flux lines, you can see some n number of magnetic flux lines are here. Magnetic flux lines are cut by the conductor or coil. What will happen? Voltage will be induced. That's the principle of operation of the generator. So there should always be a relative motion between. There should always be a relative motion between the coil and the magnetic or conductor and the magnetic field. So if there is a relative motion between conductor and the magnetic field or coil and the magnetic field, what will happen is EMF will be induced. Okay. So when EMF is induced, if the conductor or the coil has a closed path, if it is closed, okay, then current will flow through the coil. So you can see the image that I'm showing you here, it has two poles, a north pole and a south pole. In between the north pole and the south pole, we can see a single turn conductor or a single turn coil. Okay. You can see a single turn coil. Simply, you can to understand it more clearly. So you can see here this straight line, your azimuth is one conductor. This straight line, your azimuth is another conductor connected from the one other end. So this forms a single turn coil. Okay. So this is a single turn coil. Now if I rotate this coil in either clockwise or anti-clockwise direction within this magnetic field, what will happen? The coil will cut the magnetic flux and hence voltage is induced, which can be measured with the help of this voltmeter. You can see a voltmeter connected here. Similarly, if there are n number of turns in the given coil, okay. So here you can see only 3 turns are there. Okay, so there are n number of turns in the coil, and if the coil rotates within the magnetic field, then also EMF will be produced. Okay, so if the coil comes in, will the coil, and hence the current can be utilized to operate some equipment. For example, here you can see a lamp which has been connected here. So when voltage is produced, since it is forming a closed path, what will happen? Current will flow and hence this lamp will glow. Okay. So here you can see a north pole and south pole. Magnetic flux are traveling from north to south. So here in this case, what I am showing you here in this diagram, the field is stationary, field is not moving, only the coil is moving. Okay. One is moving with respect to the other. So if we have any issue, we just mention in the chat box so that I will come to know that there is some issue. You will also join with my mobile as I already told you. So if there is any issue, I'll come to you. Okay. Now, the whatever voltage that is induced, it is proportional to what? It is proportional to the change in the flux with respect to, means the flux, change in the flux means the change in the flux linking with the coil with respect to time. Okay, so as this rotates, as the coil rotates, the number of flux lines, you can see here flux lines in this diagram. You can see here flux lines in this diagram. So the number of flux lines linked with the coil. Okay. If my screen freezes, inform me. So if there is any issue, You just inform me so that I will try to rectify that issue. So here what is happening? When the flux lines are cut by this coil, EMF is induced due to rate of change of flux linkage. Means due to the flux, as the coil rotates, number of flux lines cut by the coil will change continuously as the coil is rotating. Okay, as the coil position changes, automatically the flux linking with the coil will also change because the coil is rotating, it's not stationary. Therefore, the induced voltage will be proportional to the induced voltage will be proportional to the rate of change of flux. So, 1 second, I will check that also. So I was just checking whether I'm online or some issue is there. Okay, then. So, since the induced voltage is directly proportional to rate of change of flux linking with the coil, therefore, if you remove the proportionality, it can be replaced by N. So this N is nothing but the number of turns in the coil. So as I have shown you in this diagram, so you can see there are 3 turns are there in this coil. So there can be n number of turns. So the induced voltage or the EMF, that is electromotive force. Okay, the electromotive force is equal to, it will depend on the number of turns in the coil and how much flux is linking the coil with respect to time. Okay. So you can see in this diagram, you can see the person is trying to rotate the coil manually. A person is trying to rotate the coil manually. There is a single turn coil. This is a coil. This is a single turn coil. Person is manually. We won't do this manually, but to understand the concept, I'm showing you this image. So a person is trying to rotate this coil manually. So when he rotates the coil, the flux that is linking with this coil will gradually change, and hence the induced EMF will also change. And if induced EMF is changing, then if this coil forms a closed path, then the current through the coil will also change. Okay. Now whatever EMF is induced, let us determine the direction in which it is being induced. Let us determine the direction in which the EMF is induced. So let us see the direction in which the EMF is induced. So if this thumb represents the direction of, the movement of the coil, and if this forefinger represents the direction of the magnetic field, okay, so you can see the thumb and forefinger are perpendicular to each other. So the person is holding his thumb, forefinger, and middle finger perpendicular to each other. So if this thumb represents the direction of motion or movement of the coil, if the forefinger represents the direction of the magnetic field, then the middle finger will represent the direction of the induced EMF. Okay. So middle finger represents the direction of the induced EMF. the whatever the direction of the induced EMF, the current flowing through the coil or the conductor will be same. So here in this image, it is shown induced current, not EMF. The whatever so here I can show you another image. So here you can see another image here. So in this image, you can see a right hand of a person. Okay. So with he has stretched his forefinger. He has stretched his. So you can see a person has stretched his what is it, thumb, forefinger, and middle finger. Okay. So if if the thumb represents the direction of motion, and the forefinger represents the direction of the magnetic field, then the middle finger will represent the direction of the induced EMF. So these three are perpendicular to each other. So this is known as Fleming's right hand rule. Okay, this is known as Fleming's right hand rule. So according to Fleming's right hand rule, if thumb represents the direction of motion, so if thumb represents the direction of motion, forefinger represents the direction of the magnetic field, then perpendicular to these two, all these three are perpendicular to each other. Okay, the parameters are perpendicular to each other. Perpendicular to these two, EMF will be induced. So you can see here below, this is the direction of magnetic field, this is the direction of motion. Okay, and this is the direction of induced. So see, if in our house, if you see the corner of our house, you can see length, width, and height. Okay, so length represents the motion direction. If width represents the field direction, then the height will represent the direction of the EMF. So you can see length, width, and height of our house. Similarly, on this parameter. So the direction of the induced EMF full generator is given by Fleming's right hand. Okay, it's given by Fleming's right. Okay, so now if you see this diagram, so you can see now North Pole, South Pole. This is motion. This is field. Then this is the direction of the induced EMF. So now let us see what is meant by Lenz's law. Once again. Okay then. So you can see here it is mentioned Lenz's law here. So let us see what is meant by Lenz's law. Let us see what is meant by Lenz's law. Okay, now you can see the image. So see, you can see in this diagram, there is a north pole, and a south pole. Let me see whether I can take any pen or anything. So, I can't take it. This is north pole, this is south pole. So you can see here, you can see flux lines are traveling from north pole, south pole here. Flux lines are traveling from north pole to south pole. So these flux lines, okay, which are coming out of this north pole. Now above this magnet, there is a ring. You can see a ring. You can see a ring. This is not a magnet, it is a conductor made up of conducting material. Conductor is made up of conducting material. So this ring means what? It is a short circuit conductor. It means where a short circuit means from which or end. Okay, if current starts to flow through one end, it should return back, isn't it? So it's a complete short. There's no open terminal for this conductor. It's complete short circuited conductor. So okay, it's a ring. It's a which is made up of conducting material. If you see, the flux lines are entering the flux lines are entering the flux lines are entering this, isn't it? So you can see if we have already discussed if current flows through a conductor, what is the flux will be induced around the conductor. So so you can see circular flux lines. You can see circular flux lines here. No voice. My voice is you are unable to hear my voice. I'm able to hear my voice. I have connected with my mobile. I'm able to hear. Are you able to hear my voice? Voice audible? Yes. Okay. Someone has typed my voice is not audible. That's why I'm asking you. Okay then. So in this screen, what you can see is there is a conductor, ring-shaped conductor. There is a magnet below it. Now, when flux lines are traveling through this ring-shaped conductor, what will happen? The what will happen is if this magnet is moved or this ring is moved, there will be rate of change of flux linkage, and hence EMF is induced in the ring. And since ring is a closed path, isn't it? From wherever it has started, it has returned back. It is forming a closed path. Therefore, current of I amperes. You can see a small I here. Current of I amperes will flow through this ring. So when current is flowing through a conducting material, according to Fleming's right hand thumb rule, we have already discussed that. That means right hand thumb rule. What will happen? Flux will be induced around the conductor. Okay. So you can see dotted blue color, dotted ring shaped blue color line. So the flux lines that are induced through the current flow in this ring. The straight curve lines are the flux lines induced due to this magnet. Okay, so now there are two types of, not two types. One flux is due to the permanent magnet, another flux is due to the current flow in this ring. Okay, so you just observe these arrow marks. Just observe the flux line current direction is upward. And if you observe the flux line of, the flux direction of this magnet, okay, flux direction of this magnet is upward, whereas the flux direction of flux that is increased due to the current flow in the ring is downward. Both are opposing each other. Just observe the flux due to the current flow in the ring, flux due to the magnet. Okay, if you compare those two, you can see that both are opposing each other. Therefore, according to Lenz's law, the induced EMF according to Lenz's law, okay, now according to Lenz's law, the induced EMF will always oppose the cause producing it. Therefore, E will be equal to minus N d phi by dt. What is E? E is the induced voltage in the conductor or the coil that is placed in between the magnetic poles. Okay, but it will be always opposing the cause producing it. So why it opposes the cause producing it, we can understand by the diagram that I have already shown you just now. Okay, I've been changing this slide again and again because this software is also not cooperating with you properly. Okay then. Now, so what we have seen just now is the principle of operation of DC generator. Now, if you see a DC machine, it can operate as a DC generator as well as DC motor. DC machine can operate as both as DC generator as well as DC motor. Why it can operate as both DC generator and DC motor? The reason behind that is the construction of DC generator and motor are same. The construction of DC generator and motor are same, but their function is different. What is the function of DC generator? It converts mechanical energy into electrical energy, whereas motor converts electrical energy into mechanical energy. Okay? So that is the reason. So are you able to follow the class? Still, if there is any issue, just inform me in the chat box. Are you able to follow? If you are able to follow, please mention follow in the chat box. Just type follow if you are able to follow the class. Okay, so I started my class at 2 o'clock, but it is almost 4:20. I couldn't take the class properly. If you are able to follow the class, please mention follow in the chat box so that I will be able to know that you are listening to the class and it is of some use instead of nothing. Simply taking a class without any use, it is of no use, isn't it? If you are able to follow the class, mention in the chat box. If there is no disturbance and all. Okay, then now let us see the construction of a DC machine. What did I say? Construction of DC generator and motor is same. That's why I have written two titles here. Construction of DC machine or construction of DC generator or DC motor. So if you look at this diagram which I have shown here, it is very clumsy. It is not, we won't be able to follow or understand the diagram. So that's why I'm showing you another diagram here. So if you see the second diagram, you can see a ring. You can see a big ring is there. You can see ring-like structure. So this is known as yoke. Okay, this is known as yoke. Okay, this is known as yoke. So inside this yoke, inside this yoke, you can see this red color. I don't know whether it can be visible to you or not. So you can see this. Okay. So this is known as pole. It is written pole. Okay. So what is the pole? This is pole. Okay. This is the pole. Okay. So pole will have two parts. Pole will have two parts. You can see the cylindrical portion. This cylindrical portion, it is known as pole core. Okay. So you can see this is known as pole core, this portion, and this front portion, which is broader. You can see the broader portion here. So this broader portion is known as pole shoe. So pole will have two parts. You can see this almost T-shaped structure. You can see the bottom one. You can see this T-shaped structure. You can see this T-shaped structure. It is the pole. Pole will have two parts. The cylindrical part is known as pole core. The broader part is known as pole shoe. Okay? Pole will have two parts. Pole core and pole shoe. If you are able to follow, please type pole core, pole shoe, so that I will be able to know that you are listening to the class. Okay, my voice is audible to you. Pole core, pole shoe. Okay, so this portion you just carefully observe. This is pole core, cylindrical portion. Now, broader portion is known as pole shoe. So if you see in this diagram which I am showing you here, it has four poles. 1, 2, 3, and 4. Total 4 poles are there. Now, inside there is a circular structure is there. Inside you can see a circular structure that is known as armature. That is known as what? Armature. Okay. That is known as armature. Just expand this. Okay. That is known as armature. So this is known as this whole part is known as armature. Inside armature you can see some dots, two dots, two dots. You can see throughout its outer periphery, you can see dots here, small dots are there. They are the armature conductors. What you can see here is the cross section of the conductors. Okay, so we are looking at the front view. You don't know whether your engineering drawing staff is teaching you, whether they have taught you about the front view, top view, side view, and all. If your engineering staff might have taught you that, you might be able to understand what I'm teaching. Okay, so these dots are nothing but the conductors. Since we are looking at the front view, we are able to see the cross-sectional view of the conductor. Okay, so these are the dots. The dots, you can see two dots here. These are the conductors. Okay, now you can see on the pole there is a winding. You can see some wounded wire. You can see wounded wire. This wire, it is moving like this. It is wounded around this pole. Again, it is traveling like this. It is wounded around this pole. Again, it is traveling and it is reaching there. From here, it is traveling like this. It is wounded and it is going to this. So that is almost it's approximate. It is looking like an yellow wire. So this is nothing but field wire. Okay, known as field. Okay. You can see inside circular portion. Simply observe the inside. Inside you can see a circular double circle which has been cut in equal sections, isn't it? Double circle which has been cut in equal sections. So that is known as commutator. That is known as commutator. And you can see black color square boxes here. Black color square, 4 boxes are there. Black color square boxes. Those 4 boxes are known as brushes. Okay, black color boxes, small boxes are there around the commutator. This is our commutator. Around the commutator, there are 4 boxes, black color. They are known as They are known as brushes. And inside you can see a black dot. Okay, like a bindi. Bindi is a Hindi word. Okay, so you can see a black dot. That black dot is nothing but the shaft. Okay, that black dot is nothing but the shaft. So this you can see somewhat triangular shape at the bottom of this circle below the yoke. This ring is what did I say? This ring I said it is the yoke. These are the this is the terminal box from where the field windings are taken out. Okay. So from this machine. Okay. So this triangular shaped structure which is at the bottom, that is the base on which this whole arrangement is placed. So this is the base. This triangular, of course, not complete triangle, but so it looks like somewhat triangular in shape. That's why I'm telling you. This is the base. Okay. So now let us see the 3D view of this image. This is the 3D view, three-dimensional view of DC generator or motor. Construction is same as I said. Okay. So construction, this is the yoke, yoke you see. So yoke is not in circular shape, it is somewhat cylindrical in shape. You can even call it as a body. Okay. It is a yoke or you can call it as a body. You can see some metallic color object under the yoke that is known as pole. Okay, you can see copper color here. Those are the field windings. I don't know where it is. Yeah, here it's mentioned here. This is field windings. So inside you can see this is our armature. Okay, this is our armature. This whole structure is the armature, and this somewhat blackish, dark brown color, whatever you can see, they are the armature windings. Means armature conductors which are interconnected to form the windings. Okay, so you can see base here, which are shown in the diagram as triangular. This is the base or support, stand or legs, what you mentioned, and in and bindi I said dark out inside the innermost part, that is this. So this is the whole yeah, this is the construct different parts of AC machine. For generator or motor, this is same. Okay. For generator or motor, parts of the machine are same. And this gold color, whatever you can see here, which is above the shaft here, that is our commutator. Okay, that is our commutator. So now let me show one more diagram. So you can see this diagram. In this diagram, this is our yoke. And how many poles are there? Total 4 poles are, I'm sorry, 2 poles are there. Whereas in the first diagram which I have shown you, there were 4 poles. Okay, in this diagram there were 4 poles. Whereas in this diagram there are only 2 poles. Okay, there are only 2 poles. And these are the conductors or the armature windings. You can see the cross-sectional view. If you take a pipe, okay, if you see the side view of a pipe, it will look like a rectangle, isn't it? If you see the front view of the pipe, it will look like a circle. You just hold a pipe in your hand, keep it in front of you, so it will look like a circle. So these are all the conductors, okay, whose cross section has been with armature windings, armature conductors or armature windings. Okay. So let us see each and every part. So for in order to understand the cross section of the conductor, armature conductors, so you can see this is a cylindrical structure. So you can see this is the cross section of cylinder, this is the cross section of cylinder. Now you can see this side I have mentioned dot. This side I have mentioned cross. So you know, we people go to railway station. Okay, isn't it? We all go to railway station if we want to travel. Okay, from one location to another location. Our mode of transport. Maybe we choose train as our mode of transport. So if you are traveling during night time, okay, if people are traveling during night time. So if you are waiting for your friend to uh, approach the railway station, so if the train is arriving, whether it is your train or some other train, if a train is arriving into the station, what you can see a white light glowing in front of the train. Okay, so when train is arriving towards you, okay, you can see the white light. Now, if suppose train is leaving the railway station, behind the train, you can see a cross signal. Okay, if the train is leaving the railway station, behind the train, you can see a cross signal. Similarly, when current is leaving the conductor, it is represented by cross. When current is entering the conductor, it is represented by dot. Okay, it is represented by dot. Okay, I hope you have understood. If current is entering the conductor, then it is represented by dot. When current is leaving the conductor, it is represented by cross. Okay, so current. Okay. Okay. So now if you see here, there are dotted lines around the conductor, isn't it? There are dotted lines, two dotted lines are there, dotted circles around the conductor. So what are those? They are the magnetic field that is induced due to the flow of current in this conductor. So here, what is happening? Current is entering at this end of the conductor, current is leaving at this end of the conductor. Now, okay, so current is entering. Okay, current is entering. When current is entering into the conductor, you just hold a pen in your hand, grab the point the thumb to the entering direction of the conductor, the current direction of the conductor, and grab the fingers around the conductor. Okay, if you grab the fingers around the conductor, okay, that fingers will show us the direction of the magnetic field. So, dotted lines are nothing but depending on the direction of the current flow in the conductor, these are the magnetic field flux lines that are induced around the conductor. You can see here these two dotted line arrow marks on these dotted lines is not same as the arrow marks of the dotted lines. Okay, so flux direction when current is entering and flux direction and current is leaving both are different. So, I hope you have understood. Okay. Now let us see. Let us discuss two parts of the DC generator. So different parts of DC generator. Please don't mind. I'm taking class at wrong time because of the technical issues that I had. So I don't have any issue with my mic. It's a very good mic. It's a free company mic. Okay. So, but due to this that I have been using and maybe due to my laptop, I had many disturbances too. So I don't have any other option topic. That's why I'm taking class. So let's start with yoke. You can see a yoke here. So the purpose of this yoke is it is used as the outermost cover of the DC machines, isn't it? It is the outermost cover of the DC machine. Okay. The purpose of this yoke is to provide protection from harmful atmospheric elements like moisture, dust, and various gas particles that are in the atmosphere. Okay, so because of this outermost cover, what will happen? The dust, moisture, and harmful chemicals and all they will not enter into the machine. Okay, and it also provides mechanical support to the poles. You know, inside this yoke there will be poles, so it provides the mechanical support to the poles. Okay, and it also forms part of the magnetic circuit. How it forms the part of the magnetic circuit that we can see in one diagram. I will show you that. This is it. This is the diagram. So in this diagram, if you see, the outermost ring is our yoke, and these are the poles. How many poles are there? Total 4 poles are there. There are 4 poles, and inside this is our armature. So these lines you see, these thin lines. These thin lines are the magnetic flux lines. Okay. So magnetic flux lines, they are traveling through the yoke, isn't it? So definitely the yoke must be made up of some ferromagnetic material. Otherwise, flux lines cannot travel, isn't it? Because ferromagnetic materials can be easily magnetized. So it forms the part of the magnetic field. Okay. So magnetic flux that is induced in your DC machine. So now let us see the other part, that is poles. The poles we have two parts, pole core and pole shoe. So you can see here, this is the yoke, this is pole core, this is pole shoe. Okay. So pole core, what the purpose of pole core here is to carry the field winding. Of course, magnetic flux lines will be in this pole core and shoe. Both are made up of ferromagnetic material. Okay, because flux has to be induced. We know if conductor cuts the flux, then EMF will be induced. Therefore, so here pole core carries the field winding which is necessary to produce the flux, and the pole shoe. You can see pole shoe is very enlarged, isn't it? It is broader in shape. Okay, pole shoe is broader in shape. So the pole shoe is its area is enlarged for the armature core to come across the flux which is necessary to produce the large EMF. Okay, it helps to produce what? It helps to produce the large EMF. So in order to produce large EMF, pole shoes are necessary. It will only distribute the flux within the machine. Okay, in order to uniformly distribute the flux within the machine, okay, pole shoes are essential. Their shape is somewhat like that because of that. Next is magnetic field, which I have already told you. This is the magnetic flux that is induced. So in the poles, okay, and the flux lines, magnetic field that is induced in the poles will cut the armature conductors and they will return back. Okay, so they are also the magnetic flux lines also form a closed path here, isn't it? They are forming the closed path. They are like concentric circles. Magnetic flux lines are like, you can see all these ring shaped structures are the magnetic field. Okay. So you can see here on the diagram. So you can see there are two poles here. Okay, one pole acts as pole, another pole acts as south pole here. So flux lines, you see these flux lines. Only one flux line is shown here so that you can understand the concept. From north to south, flux will travel. White dotted line you can see. From south through the core, it is written back to the north. Again, another dotted line you can see, north to south dotted line. It is the flux line that is traveling from north to south, from south to north to the core. It is written back to the north. Okay. Similarly, if there are four poles, you can see the poles are alternative nature. You can see if this is north, this is south, this is north, this is south. Okay. So there are alternative poles are there. So from north, the flux will travel from north to south. To the core, it will return back to the north. From north to south, flux will travel like this, and it will not south north to the core, it will return back, and so on. Okay. This is how the flux lines will travel. And in the core. In the core means in the yoke. Okay. So now let us see what is meant by field winding. So field windings are placed around the pole. So this is your pole core, this is our pole shoe. So around the pole, field windings are placed. I have an image here. You can see here. This is it. This is the pole core. This is our pole shoe. And these copper wires you can see, they are the field winding. Okay, they are the field winding. So I have a colorful image here for field winding. This is it. This is pole core. This is pole shoe. So you can see gold color. That is our field winding. That is our field winding. Okay. So field winding, it is placed around the pole core. Okay. To carry current, due to which pole core on which these field windings have been placed. the pole core gets magnetized. As I already told you, take a ferromagnetic material, wound a copper wire around it, you allow current to flow through the copper wire, that ferromagnetic material gets magnetized. Similarly, when current flows through the field winding is made up of copper. Okay, so because copper is a good conductor. So when current flows through the field winding, what will happen? What will happen is poles get magnetized. Okay, poles get magnetized. So the field windings are wounded around each and every pole. You can see here. You can see 1, 2, 3, and 4. 4 field windings. You can see me. They are wounded around 4 poles here. Okay, so they are wounded in certain pattern and such a way that if this pole acts as north pole, this pole will act as south pole. If this is south, this will act as north. If this is north, this will act as south. Okay, so they are wounded by the engineer or the technician who is manufacturing this device. He will move in such a pattern that if one pole acts as north, the pole besides it will definitely act as south. If this is acting as south, other will the pole besides it will act as north. So, okay, so this is our black color structure is what? Black is the yoke, inside pole and field winding. This is the base. Okay, so this is our armature conductors, commutator. Okay, so this is all about field winding. Sorry. Now let us see what is an armature. This is our armature. Let us see the armature. Armature. So armature, if you look at this diagram, you can see armature is cylindrical in shape, isn't it? Armature is cylindrical in shape, and you can see on the outer periphery, outside of the cylinder, there are some cylindrical holes. They are digged outside. Okay, there are some holes digged outside along the length. You can see. So those holes are known as slots. These holes are known as slots. Okay. So in these slots, conductors are placed. Okay. In these slots, conductors are placed. How they are placed, you can see here. Within the slots, these are the conductors you can see. Okay. These are the conductors which are placed here. So I have better diagram here. So this is it. This is the armature. This is the front view of the armature, and these are the holes. I have better images. So this is my armature. On the outer periphery, what is it? Holes are digged. Why holes are digged? In order to place the conductors. Those conductors are known as armature conductors. Okay. So armature conductors are placed within these holes. So armature will have two parts. Armature will have two parts. One is armature core, another one is armature winding. Armature conductors are nothing but armature windings. Armature conductors are connected to form a coil. That coil is known as armature. Okay. So this armature is also made up of aromatic material to allow the flux line to flow through it. So uh, if if in any material resistance is low means more current can flow. Okay. So if any material, if I say reluctance is low, okay, means more flux can flow. So flux reluctance opposes the flow of current. I'm sorry, reluctance opposes the flow of flux, and resistance opposes the flow of current. Okay. So resistance property is what? Resistance is the property of a resistor which opposes the flow of current, whereas reluctance opposes the flow of flux. So the material which is used to manufacture armature or yoke or poles, those materials should have low reluctance path. Then only more flux lines can travel through them. So this is our armature along with the armature windings and the slots in which armature windings have been placed. So this gold color structure, what you can see is a commutator. I have a better image somewhere. Where is it? So this is our commutator, isn't it? This commutator, this is our shaft. So let us discuss about the commutator. Let us discuss about the commutator. So you can see here, this is the armature windings which are placed down. So this is it. North pole, south pole, north pole, south pole. They are the free, what is say, poles. Okay, this is our armature. These are the dotted like cross-sectional view of the conductor. You can see there is a single turn coil here in the armature. This is double turn coil in the armature. These are the armature coils are placed in the armature. So here some technician has already designed the armature. He has already placed the armature windings in the armature. Okay. Now let us see what is meant by commutator. Commutator is the one which will collect the current from the armature windings and it will convert that whatever current that is flowing, okay, in the armature windings. Actually, it is sinusoidal in nature, but our machine is what? DC machine. DC machine means it should not be alternative in nature, isn't it? The voltage induced or current flowing in the conductor should not be alternative in nature. Okay. Is anyone in the class? You are in the class, please just raise your hand. If anyone is listening to the class, please raise your. Seven. So here, the commutator, what is it? It just collects the current and it converts that bidirectional current or voltage into unidirectional. Okay, so it converts the bidirectional current into unidirectional. You can see whatever current that is flowing in the conductors is actually alternative in nature. This is sinusoidal waveform, you can see here. So it is sinusoidal in nature and it is converted into unidirectional with the help of the commutator. Okay, so commutator will have a layer of mica. It's made up of mica, thin layer of mica, which has been insulated. I'm sorry, segments are insulated on mica, thin layer of mica. They are connected to the armature wire with the help of bricks. It has so this is commutator which is connected to the armature conductors. Okay, next brushes. Brushes. So brushes they collect. Brushes are the square shaped black boxes. Okay, square shaped black boxes. So these boxes will collect current from these split rings. Actually, split rings. Uh, this you can see blue color shape, blue color whatever half circle or half cylindrical shapes are there. They are known as split rings. Okay, so they collect it from them and they give it to load. Brushes to color. You can see another image here. So this is it. They are just attached to the split rings. So you can see I have mentioned here commutator. They are just attached to the commutator and they will just collect and give it to the load which is to be operated. Next, bearings. Bearings are um, or they are placed within the armature, so there is not avoid friction while the armature is rotating. Okay, not avoid friction while the armature is rotating. So next comes the important part, working principle of DC generator. So let us see the working principle of DC generator. So not understand that, just look at this diagram. You can see a coil here, a north pole and a south pole. Coil, north pole and south pole are there. So, so this is it. So what is the purpose of function of generator is to convert mechanical energy into electrical energy. So when this coil is rotated within the magnetic field, what will happen? EMF is induced, which is alternative in nature. That EMF is converted into DC with the help of a commutator. So actually there will be slip rings, which are replaced by slip rings later on to convert AC into DC. Okay. So now let us see how this, what is the working principle of DC generator, how EMF is induced. For that, I have an image, this image. You can see here in this image, this is North Pole, this is South Pole. This is North Pole, N, you can see N, and you can see S, North Pole and South Pole. So inside North Pole and South Pole, this is our coil, single coil is placed here. You can see a single coil here. So which is whose position is zero position, we can say. Okay, so position, its position is zero position. Okay, so the it's in zero position. Okay, so the coil is right angle. Okay, the coil is right angle to the magnetic flux lines. Okay, so the angular displacement between the coil and the yellow color dots that you can see are the magnetic flux lines. So yellow color dots are the magnetic flux lines, and this is our coil. So the position, this position is known as zero position. So and in the zero position, when coil is right angle to the flux lines, okay, the voltage that is induced, okay, voltage that is induced will be zero. You can see here a waveform. So the voltage induced is 0 volt. Now let us rotate this coil to 90 degrees. Okay, let us rotate this coil to 90 degrees. And the coil is rotated to 90 degrees. Okay, the coil becomes parallel to the flux lines. Okay, coil becomes parallel to the flux lines. So the maximum flux lines will link with the coil, and hence maximum EMF is induced. Okay, rate of change of course, not maximum flux line, means the maximum flux lines are cut by the coil when the coil is at 90 degrees. Therefore, the maximum EMF is induced. So at 90 degree EMF, you can see here, is maximum. The voltage is maximum in wave. Okay, when the coil is rotated in 90 degrees, so you can see the previous position has reached. Okay, first position, position 1, position 2, position 3. In this position, what will happen is minimum the rate of change of flux linkage will be minimum. Okay, of course, more flux with the coil because it is parallel to the flux lines. Okay, but rate of change of flux linkage will be minimum at position 3, that is at C. Therefore, at C, the voltage will become 0. Okay, now see, this is our red color side, this is black color side. When it is rotated clockwise, red side has gone to the right side. When further it is rotated clockwise, red side has gone. Now at position D, what has happened? Now red side is on the left side, black is on the right side. Okay, if you compare position D with B, okay, both are same position, but coils have interchanged. Coil positions are interchanged. Since the coil positions have interchanged, therefore the voltage will be induced in negative direction. Okay, and since rate of change of flux linkage will be maximum at this position, the EMF induced is maximum in the reverse direction. Okay, further, when coil is further rotated, okay, when the coil is further rotated, so you can see here red is above, black is below. So position A, again position A has reached after position, okay, again position A has reached after position D. Therefore, the induced flux, induced EMF will be 0. Okay. So this is how the EMF is induced. So which is alternative in nature. So as the position changes, okay, as the position of the coil changes, automatically the induced EMF the amount of induced EMF will change. Why? Because the rate of change of flux linkage with respect to the coil will also change. So as the rate of change of flux linkage increases, the induced EMF increases. As the rate of change of flux linkage decreases, the induced EMF also decreases. Now, the induced voltage in the um, generator is alternating nature, but we don't want it is a DC generator. We don't want the alternative voltage. Therefore, there are instead of using slip rings, okay, instead of using slip rings, on a slip rings, split rings are used. These are the split rings. Okay, instead of using slip rings, split rings are used. Okay, so alternative voltage will become, okay, unidirectional voltage. Alternative voltage will become unidirectional voltage. Of course, when you look at this, it is also, it's not a pure DC. Okay, it is known as pulsating. Okay, it is not pure DC. It is known as pulsating. So when AC alternating voltage is induced, these are the slip rings. These two rings you can see they are the slip rings. Okay, so those slip rings are replaced by, you can see red color half circles here, by replaced by split rings to convert AC voltage to DC voltage. The induced EMF or voltage in your generator is alternative in nature, that is converted into uh, unidirectional with the help of split rings. You can see split rings is shown here. So I'm going to finish within 5 minutes. I'll conclude this DC generator. So now let us see the EMF equation of DC generator. Okay, EMF equation of DC generator. So let us assume, if you know your generator, just now I have discussed, there will be number of poles. If P number of poles are there, if P number of poles are there, if phi is the flux produced by the poles, okay, flux that is induced in the poles is phi. If n is the speed of the armature at which armature is rotating, coils are rotating, isn't it? So coils are placed in the armature, so they are rotating. So they are rotating with n speed. If z is the number of armature conductors, if the total number of conductors in the armature is z, if A is the EMF induced, then A is the number of parallel paths, okay, which are formed by the interconnection of the conductors. Okay, so if A is P, A equal to P or A equal to 2. What is A? A is the number of parallel paths. Okay, A is number of parallel paths. Okay, so we are not going in depth into this subject. So otherwise, I might have explained more. Okay, we are just actually EMF equation is not there in your syllabus, but I just wanted to tell you. So just to listen, the number, if A is number of parallel paths, A will be equal to P for there are two types of windings, lap winding and wave winding. So A will be equal to P. P means number of poles. A will be number of parallel paths will be equal to number of poles. If it is lap winding, number of parallel paths will be equal to 2 if it is a wave winding. Okay. So we are not going in depth. So we already know E is equal to d phi by dt. Okay. And of course, if I go in depth, it will be confusing for you. So just I will not discuss much. So just remember E is equal to phi into Z into N into P by 60A, where phi E is what? E is the induced voltage. Okay. And phi is the flux. And Z is the number of conductors. N is the, what is N? N is the speed at which armature rotates. So earlier I told you N means number of turns. Okay, yeah, turns of the coil. Okay, so for number of turns of the coil and for the speed of the armature, for both N is the notation. So don't confuse here. N is not the number of turns here. N is the speed of the machine. And here P represents the number of poles and A represents the number of parallel paths. Okay, that's it. I hope there was no disturbance during the class. Was my voice audible and clear? Were you able to follow?